Okay, we're going to finish 9.2 with the P-series test. The homework for P-series is going to be 33 through 37. And then I added some that's not on Canvas yet. I want you to do 69 through 79, which puts stuff together and keeps you flexible here. Limber, that's the word I was looking for. So here we go. When you see an infinite series that has an n to the power, P stands for power, I guess. I'm going with it. This is called a P-series. P-series are very, very, very important. You notice that you're dividing. You have a constant. It doesn't have to be a 1. Usually, if it's not a 1, you just factor it to the outside. Because if it's a constant, then it's been distributed throughout this sum. You can undistribute it and factor it out. But you notice that the n is in the bottom and it's being raised to a power. Now, P can be anything, positive, negative, fractions, whole numbers, doesn't matter. So remember, for a series to be convergent, the terms in the series need to get smaller and smaller. But just because they get smaller and smaller and eventually go to 0 does not mean that the series converges. There is one very special P-series. We're going to start with that, the harmonic series. The harmonic series is the series where P equals 1. So the series 1 over n diverges. You have to get this. Okay? So even when you start, even though the thought bubble over here, even though the limit as n goes to infinity of 1 over n equals 0, that doesn't tell you anything. The nth term test only can tell you if it diverges. Just because these terms are going to 0 as n goes to infinity doesn't mean that your series converges. It diverges in this case because it just doesn't go to 0 fast enough. Okay, for a P-series to converge, P must be greater than 1. If it equals 1, it's harmonic. If it's less than 1, you're out. It can be 1.00001 and it will still converge as long as it's greater than 1. P-series are very easy and you just got to watch it. Just because it goes to 0 doesn't mean that it is convergent. Notice that the base is the thing that's changing, and the power stays the same, which is a little bit different from what we're used to. But you can do the integral test on 1 over n to the p and prove that it converges for p greater than 1. So let's try some practice problems here. All right, number 34. We have n equals 1 to infinity of 3 over n to the 5/3. Watch me. 5/3 is greater than 1. This is a convergent P series. You have to tell me what kind of series it is. And in the case of a P series, you have to show me that P is greater than 1 and tell me that it converges. I'm going to be very picky. Sorry. Let's try 38. N starts at 1, goes to infinity, 1 over n to the nth. Well, at the very beginning, n equal, the power here equals 1. But as you move out, once you get past that, for n greater than 1, it converges. And remember that rule at the bottom of the page that I talked about, P series, because n goes to infinity. The rule on 60 something, hold on. The rule at the bottom of 609 says that as long as you get past a certain counter and your series starts to converge, then you can say that the series converges, even if it misbehaves for small values of n. As long as it's convergent for large values of n, you're good to go. One more practice problem. Let's do number 36. Number 36, 1 plus 1 over cube root of 4 plus 1 over the cube root of 9 plus 1 over the cube root of 16. What the heck is going on here, huh? Cube root 25. It looks to me like we have perfect squares under the radical. So if you think about it, this is 1 plus 1 over 2. The top is the power, the bottom's the root, plus 1 over 3 to the 2/3, plus 1 over 4 to the 2/3, 1 over 5 to the 2/3. So, what's P? P is 2/3. It's less than 1. Now, what about that first term? Isn't that 1 to the 2/3 in the bottom? Yeah. So, n starts at 1 and goes on and on and on. So, we have the sum from 1 to infinity of 1 over n to the 2/3. And that makes this a divergent P series.